Good morning to all of you. I welcome to all the participants and our invited guests for the second day of the Indo-US webinar. Today we will have 4 keynote lectures. 3 keynote lectures will be delivered before lunch. Then we will have the technical break, and the last session will start at 4 o'clock. And in the evening at 5 o'clock, we will close officially this webinar, and the valedictory address will be delivered by Professor Ganguli and Professor Chari. So today I am very fortunate that Professor Ganguli accepted my request and agreed to chair the session in which Professor Mao will be the keynote lecturer. So I request Professor Ganguli to please chair this keynote session. Sir, please.
Good morning, Tokeer. Good morning, Professor Mao, and good morning, everybody else who has joined online. I am thankful for Tokeer to ask me to chair this very important session, and would be very happy to introduce Professor Mao, Professor Yuanbing Mao, who is currently a professor, department chair of chemistry at Illinois Institute of Technology. So it is IIT. So like we have IIT, we have IIT Chicago. Now Illinois Institute of Technology Chicago is a well-reputed institution, and he received his bachelor's from China, from the Institute of Chemistry. Again, a very good institution. I have visited the Chinese Academy of Sciences, and very, very good research goes on. And got his PhD from Stony Brook. He was a postdoctoral fellow at UCLA, University of California at Los Angeles, and has got several awards: the US Department of Defense Young Investigator Award, the Outstanding Mentorship Award from the Council on Undergraduate Research. He's a recipient of the US DOE Visiting Faculty Program, and many grants from the American Chemical Society, like the Petroleum Research Fund of the US National Science Foundation, the Air Force of Scientific Research, from DARPA, from US Department of Agriculture, and the Bill and Melinda Gates Foundation. His research is mainly on designing advanced nanomaterials, and currently he is focusing on development of facile and reliable methods for complex oxide nanomaterials, their properties in the areas of optoelectronics, energy conversion, and sustainability. He has more than 125 peer-reviewed journals, as well as book chapters and patents. So highly distinguished professor, and we welcome him and request him to deliver his lecture today. Professor Mao.
Professor Ganguli, thank you very much for the introduction. Very nice. Thank you very much. And let me share my screen. Okay, great. So I hope you can see it, right?
Yeah. Yes. Sure.
Cool. See where I can get my. Trying to see whether I can get my pointer, or maybe just use my cursor.
You can use your cursor if you are not able.
Yeah, okay. I will try to use my cursor. I'm not familiar with this one. So anyway, so that's fine. Okay, so yeah, today I'm going to thank you very much for everyone and for your attention. And I'm going to talk a little bit about the three-dimensional nanostructured catalysis for water splitting. So that will be my focus. And yeah, so I'll start with, there's a great need for more energy, especially electricity, right? So there's a petawatt scale global electricity consumption, and it's already there, right? So to meet this demand, and then definitely we need a sustainable global energy demand, sustainable energy, and also we need to consider the cost and environmental footprint as well. Especially right now, this environmental issue is really a big problem, right, for everywhere. It's also globally, and here actually you can see, where the electricity consumed the most, right? North America and Europe and Asia as well. So definitely, that's why it's so important for us. And this webinar series is really came on time for all of us involved and to see what we can do. And so in terms of catalysis to meet this sustainable energy demand, so there are different ways to meet that demand. And there are solar energy, wind, hydrothermal energy, and so some people consider the nuclear energy also as sustainable, but there are different type of views on that. So we are not cover that today, but in a couple of days I will talk a little bit about that as well. So once we have this energy, right? So how do we take this, get the solar energy especially? And then there are different ways, right? And then through different type of catalysis processes. One is electrocatalysis and also photoelectrocatalysis, and also there is a thermocatalysis as well, right? And then we generate the chemicals and the agents, and then we can use them, in different ways, and also it can be transported to where they are made. So that's the whole process, right? Today, I'm not talking about the thermocatalysis, and I'll mostly focus on the photoelectrocatalysis. In terms of the generated electricity, and then of course there will be need batteries, and also there are some studies on supercapacitors. So I will mention a couple of slides on that aspect. So, and then related to the photo catalysis, so I will start with this, right? Because if we consider our society, right? So mostly the energy came from the solar energy driven artificial photosynthesis. And so the question is, how can we use that, especially for the artificial photosynthesis process? In here, that's what I'm trying to focus on. So for the photosynthesis, we have, CO2 and then water, and then the plants will take that and also take the solar energy and then generate the sugar and the oxygen, right? So that generate, the chemical energy. And but then for the artificial photosynthesis process, especially for water splitting, so we have the water, and then it also takes the solar energy and they split into hydrogen and oxygen. That also store the chemical energy. And but that process is not easy, right? Just by itself, then it will it's not easy process. That's why we are trying to develop catalysis and to lower the activation energy, and they make this process more feasible. So one way to do that is we use a catalyst, and especially semiconductors. And of course, this process is quite complicated, right? So if we take some time to look into this process, and then we will see that. Oops. Okay, so now it looks good. Yeah. So first, the process is, of course, right. There will be photo absorption, and the catalyst, the catalyst absorbs the photons, and then it will generate the electrons and the protons, and so that will have sufficient potential for water splitting based on the band energy, band engineering. And then, of course, right, they generated the electrons and the holes. We need to prevent their recombination. So that's also one thing we need to consider during the process. And then, so to do that, right, so we need to keep them separated, and they migrate to the surface reaction sites, and that's what it shows here, right? So, and then they will generate hydrogen and oxygen during the processes. So there are different type of catalysts for that process with semiconductors, and then sometimes there is also catalysts as well. So that's the basic process. And in the literature, and there are different ways to show these processes. You probably see this before, right? But if we consider the chemistry aspect, right, the process is based on the oxidation. Okay, so is the oxidation, right? So we generate oxygen, and then which is a full electron process, which of course is not easy process. And then in terms of the reduction side, right, then it generates hydrogen. The overall reaction is water split into oxygen and hydrogen. And we know the reverse reaction is very easy, right? But that tells us this reaction is very challenging. That's the other way to understand this. So in terms of the semiconductor, the catalysis, right? So there is a lot of things for us to consider, because the interface will be a solid liquid interface, right, with the electrolyte, and so then the generated the electrons and the protons, how do we separate them, how they transport quick enough, and so those are the things we need to consider. But if we use a simple equation to show that, I mean, this equation is not really that simple. It looks simple. So the first is, how the protons being absorbed, right? So there is the efficiency as well, and then the generated charge carriers, how fast, how efficient they can be separated, and how fast they can transfer to the surface of the catalyst. So, so in this, in my following presentation, then I will consider these three aspects and how to solve this how to improve the efficiency. So that's what I want to start it with. And then the other thing I want to mention is today what the examples I'm going to present is actually not to develop new materials, new catalysts, but I'm more focused on how to solve, how to improve the efficiency by structure engineering. So I know I'm a chemist, but I'm in this aspect, I'm more like an engineer. So just bear that in mind. So in the other way to look into this is get back to the materials, right? Nanostructured materials, of course, it has a large surface area, and for catalysts, that's very critical, because most of the catalytic reactions happen on the surface. So that's why in the recent years, nanostructured materials have been studied a lot. And there are different types of nanostructured materials. It depends on how we categorize them, right? So here, I'm trying to show you in different, based on their dimension, right? So if they are spheres, we call them as a 0 dimension. And if they are nanowires, nanorods, nanobelts, those type of things, then we consider them as 1-dimensional. And if they are sheets or plates, and then they are called the 2-dimensional, and then they are 3-dimensional ones as well. 3-dimensional doesn't mean they are solid, completely solid crystals. And of course, they have inner surface areas as well. So that's the 3-dimensional. If we consider this type of ways, right, and also considering how fast the generated charge carriers can be separated, can be transported, and then definitely the nanoparticles will not be good options, even though they have a large surface areas, right? So this type of 1-dimensional structures may be more efficient, right? Because the charge carriers will be much easier to transfer and also be separated, because they are unique structure. And the more so, we also want to avoid the interface as well. So that's why in this paper, and they has this the future 3-dimensional electrons, right? So you can see this, they are all connected while they have large surface area. There is a lot of empty space, so it will have very high interfacial areas with the electrolyte. So that's why this is the drain structure we are trying to get into. And also that's related to example that I'm going to show you today. Okay, so but how do we do that, right? Especially if we are thinking about to make a structure like this three-dimensional in the nanoscale, right? So that's of course it's not the easiest thing to do, but we have found a couple of ways as well. The other thing I want to mention about this type of future three-dimensional structure is just think about our metropolitan, the mega cities, right? Here I mentioned about I'm showing some pictures about the Manhattan and in New York City, and then New Delhi and Beijing, and as well. And then you will see that, right? When they are large populations, right? What our human society do, right? They build high skyscrapers, right? So you can accommodate more people, right? So for this type of three-dimensional electrodes, so that's the way I've been, we are thinking about, but we are, of course, we are doing this at a much smaller scale, right? So that's the challenge part. So the first example I want to show you, or to mention to you a little bit earlier, in terms of the energy storage. So we thought about this, and then we planned, we designed this type of structure. We call this the nano forest, right? So let me break it down you slowly, and how do we make this type of nano forest. So first, so we have a substrate, and then we make some zinc oxide nanoparticles, particles as a seed, right? Basically, we coat it on the substrate, and then we try to grow nano wires, nanowire arrays on the substrate. And so this aspect, at the time, there are a lot of reports already, so it's relatively, it's a well-studied system, and so we just take the synthesis procedures from literature, and then we could repeat it easily. So then the next thing is, so we've been thinking about this, right? These nanowire arrays are wonderful. Okay? They are, they already have large surface area. They are nanowires, so there's not much interfacial resistance. And but then you can think about it, right? There's still a lot of empty space between these nanowires. So we were thinking about, can we grow some branches, okay, along these nanowires? So that's what we did. The trick is just repeat this first step, right? Here, the nanoseeds would deposit on the substrate. Okay, so basically it's a flat, right? And then for our processes, then what we did is we do another step of nanoseed deposition on the surface of these nanowires. And then we repeat this hydrothermal synthesis process, and then we grow some branches. Of course, right? Those for the second step, the zinc oxide nanoparticles, the seeds will not, just go on the surface, right? It also will go to the bottom of this nanowire arrays. Okay, that's the next thing I want to talk. When we talk about the next step, next example, right? So for now, this thing works, and then this is the details in terms of the hydrothermal synthesis. So we use the zinc nitrate as the precursor for zinc oxide. And then we use HMTA. This is actually the formula of the HMTA. And then we use also PEI as well, and then ammonia. So that's the process. The reaction is really mild, 60, 90 degrees Celsius for a few hours, so it's easy to handle. Of course, there's a lot of controls, a lot of repeats as well, a lot, some details, right? Of course, for supercapacitors, zinc oxide, of course, is not good, right? Material. So what we did is we coated this with manganese oxide. So how do we do that? Is basically based on this redox reaction between the permanganate and also carbon. So what we did is first we coated this zinc oxide nanostructures, okay, either nanowires or nanofores. So we use both because we want to compare, which one has a better performance. So we coated them with carbon, and then we use this reduction process. Then we convert the carbon into manganese dioxide. So basically, this type of zinc oxide nanostructures becomes the manganese oxide coated zinc oxide nanostructures, either nanowire arrays or nano forays. So I don't want to show you the details in terms of how this performance improved, how the measurements was done. But what we did is we see that the nanoforest provide increased surface area and more active materials. So the nanoforest, it serves as a novel non-planar electrode geometry to enable both energy density and the power density. And then what we did is actually, I want to get back to this. So this type of nanoforest has 5 times higher performance than the nanowire arrays. So the nanoforest, actually serves as a highway for effective electron transport. Because of that, so then we submitted this to chemical communication, and then we've been invited to prepare a cover, and so that's what happened. I don't want to spend too much time on this, but I want to move to the next one. Really, that's what was the focus today. So again, get back to the artificial photosynthesis is really think about the nature, right? We can learn from nature, and we can think about, right? For those trees larger and taller, right? They have a lot of branches, and also those branches are long, right? So what we can learn from this, right? So it will help for us to improve the artificial photosynthesis, right? Basically here we focus on the water splitting, okay? So that's what we learned, right? Based on the success we had, in the example which I just showed, so we've been thinking about, right? Yes, we can grow those nano branches on the zinc oxide nanowire arrays, right? So can we tune the branches in terms of the length and in terms of the diameter, in terms of the density, right? So again, right, this is a hydrothermal synthesis process. While at the time, there are some studies, try to tune the nanowires arrays in terms of the density, the length, and the diameter, but not for the nanoforest. So that's what we did, more focused on the next step, right? How to control the branches. Okay, so here, you can see that at least there are several parameters, right? I just when this week when I prepared this lecture, and also because nowadays, right, people use machine learning a lot. So I'm thinking, yeah, maybe this is a topic really for machine learning. So here, what I want to say is, you can see that there are, several parameters which we can play with, right? We can adjust the zinc oxide, the zinc nitrate concentration, HMTA concentration, PEI, and ammonia concentration, right? And also the synthesis temperature and the time as well, right? But here, what we did is we only focus on 2 parameters because that's already complicated enough, as I will show you a little bit in a little bit. So this is actually, this slide is just a summary, and you can see here the x-axis shows the concentration of ammonia, which we which we studied. And then the y-axis here shows actually the PEI concentration. And the most important thing here you can see is how the original zinc oxide nanowire arrays, how that changed, and also how the branches in terms of the diameter and the length varied. Okay, so you can see one, or just focus on a couple of things here, right? You can see under this condition, and then the original zinc oxide nanowires actually changed, especially on the tip. Okay, that means there is actually something happened, right? You know, in terms of the aging, because the zinc oxide is not really, you know, stable enough under the synthesis conditions we have in here, right? And then you can see sometimes, you know, the branches are pretty short, right? Sometimes the branches are actually pretty dense, but they are still short and thick and big, right? But then if you look at this one, and then you will see those branches are pretty dense and long and pretty small, right? So it gives us, you know, pretty nice image that, you know, we really can tune just to change the concentration of PEI and ammonia, right? Just like a couple of weeks ago, actually, I was reviewing another manuscript, and I saw that people are still interested in this process, and they are changing some other parameters, and so that's great to see that. And then, of course, to get this summary slides here, you know, we did a few things I want to show you quickly, so you know where it came from. So the first thing we did is we didn't add PEI, and of course you know, here, right, we have zinc nitrate and then HMHCA in there, okay. But when there's no PEI, but we changed the concentration of ammonia, and then you will see that, you know, how the branches changed, and also how the original zinc oxide nanowire, you know, the shape changed, you know. So here the left column shows the side view, and then the right column shows the top view of those nanostructures. And so it is obvious, right? They are different. Okay, I don't want to go to the details. You know, we did have the detailed information in terms of the length and the diameter. But there's one thing I want to show you is we did taken X-ray diffraction patterns from these samples, and then we used so for this part it's important to quantify the degree of crystallographic preferred orientations. So for those of working with crystals, and there is a Harris texture coefficient, TC. And so what we did here is basically this is equation how it works. So we know this peaks has different orientations, and we use this formula to do the calculations. So this I and this I long, basically they are the peak intensity, right? And then N depends on how many peaks we use in the calculations. So here, based on this figure, you can see that we picked these 3 peaks. So basically N equal to 3 here. And then one thing I want to show you is quickly, it's like you can see that 002 peak is actually, you know, initially the intensity increased, and then to this part, then after past this part, it will decrease. While the other 2 peaks, it has the opposite trend. So why is that, right? You know, I just want to show you some chemical equations, and then you can understand how complicated this process would be. These are just some proposed reactions. We don't actually know which one actually is preferred, okay? but definitely under different conditions. Here, with a different ammonia concentration, definitely some of these reactions, was dominant. So initially, right, because we didn't add PEI and ammonia, so that basically the HMATA will play the role, right? Basically, it generated ammonia, and so that provides the basic conditions, right? Then zinc react with this and generate zinc hydroxide. It decomposes into zinc oxide. So that's that's whatever if we have the basic condition and also not strong enough, then we can generate zinc oxide, right? But then we add more ammonia, and then that's what the aging happens, right? And then PEI also have a similar function, while PEI also can be act as a capping agent. So that's what the synergistic actions happened. Okay, so this part is basically we didn't add a PEI, right? But one thing we can notice that is under certain conditions it works best, right? So that's why we picked the condition for in terms of the ammonia concentration. So basically, this is so before I go to that, so I want to point out the other thing as well. So in this part, we didn't add ammonia, right? So we changed the PEI concentration, and then you will see that these branches are actually not very good. So PEI in certain way, just without ammonia, it doesn't work well if we want to grow branches, right? Then the next thing is, okay, now we get a little bit idea, in terms of the ammonia and the PEI, how their concentration affect the branch growth. So the next thing is because okay, let me get back to here. So here you can see that it looks like, this one, when the ammonia concentration is equal to 0.15 molar, the branches looks nice, and those branches are thin enough, not like the first one. So that's why we picked this ammonia concentration, and then again we varied the PEI concentration, just like we did I showed you a little bit earlier. And then the interesting thing is now we can see, there's quite nice branches grow on this the zinc oxide nanowire arrays, and also the original zinc oxide nanowires being cut and being etched. So that's the other important thing. So that's how we get to this summarized slide. So with that, right, we couldn't really, study the photocatalytic performance of all of these samples. So we picked two representative samples. Basically, this one, which has pretty, so HA5, which have, quite short branches. So basically, let me get back to this slide. So we have an HA5 and HAP3. So these ones, those branches are dense, but they are pretty short and thick and big. So we call this as a brush, like, really like a nanostructured brush, right? And then the other one is, those, you can see these branches are pretty long and they are not straight. Okay, so we call this a willow-like because they are really like the willow leaves. And of course, we did more, high-resolution TM studies, and we just wanted to understand a little bit more. So definitely they are crystalline, and also we try to actually these two high-resolution TM images are from the branches, not from. Of course, now it's difficult to get the high-resolution TM images of the original zinc oxide nanowires, right? So these are actually focused on the branches, and you can see that they are synchrocrystalline, and these all grow along the 002 direction. So that gave us a pretty good idea. But the next thing I want to ask you, okay, now we made this different type of nanotrees, okay, or sometimes they call this a nanoforest, right? When we also have this one-dimensional nanowire arrays. So basically, if we compare these three samples, right? So I have a question here, is which sample has the highest transmittance in the visible range? Okay, and then in terms of reflectance, and then how about the absorption, right? If we have, say, we have solar light, right, hit on them. Maybe give you 30 seconds to think about it, right? And also think about, how do we confirm, right? So what we did is actually, we use a UV rays, and actually we can really confirm that. Of course, so the first thing is we can just take the transmitters. Okay, then you will see here that the willow-like zinc oxide nanoforest actually gave the lowest transmitters. Okay, and then the zinc oxide nanowire arrays give the highest transmitters. That means they are more light goes through the sample, right? And then also we can take the reflectance, and then you will see that the zinc oxide nanowire arrays give the highest reflectance, and then the willow-like. Oh well, yeah. We published it before, but I see there's a typo. Okay, the willow-like zinc oxide nanoforest actually have the lowest reflectance, right? So we know that, right? If we take the reflectance, we subtract the transmittance and the reflectance away, and then we get the absorption, right? So based on that, and then we will see that the willow-like zinc oxide nanoforest actually gives the highest absorbance, and then the zinc oxide nanowire arrays gives the lowest absorbance. So how do we explain that, right? If I show you schematically, then that will be much easier, right? So this type of nanowire arrays, because they are not dense enough, right? So the transmittance is highest, right? And also because of the end of these nanowires, so they could have quite a higher, reflectance, right? While for the nanowire, the nanoforest, right? There are a lot of branches. Once the light get in, and those lights will reflect, in between them, and then, the light can stay there for longer time, right? So that's why the absorbance is also highest. Okay, so that's how we look at the optical property before we take the electrochemical performance. So this is what the photoelectrochemical performance of this zinc oxide nanostructures. And also, so there are different type of measurements, right? For those of you who work in this area, you will see that. But in general, a lot of times, this is one. Okay, let's look at this one first in the panel A, and we'll see that the photocurrent density, that's one of the most important parameter which we take. So here we look at this this three samples again, and also so these three samples under the solar light. And then we also compared with the sample which is in dark. So that's why you see four curves here, right? In terms of the potentials, then we started from -0.5 to 1.2 volts. And then you will see that, definitely the willow-like zinc oxide nanoforest as highest photo current density, right? So then, we can convert this to conversion efficiency, right? And again, you will see that the willow-like zinc oxide nanoforest actually gives the highest of conversion efficiency. And so, of course, right, I just showed you from the optical property aspect, right? It helps us to understand why the willow-like nanoforest would have the best for the electrochemical performance, right? But there are other factors as well. So this one thing is we look at the resistance, the charge transfer resistance, and then we can see that the willow-like zinc oxide nanoforest actually has a very nice half curve. So that gives us, and also this resistance is actually the lowest compared with the other two samples, right? And then we also look at the conversion decay time as well. And we can see that, there are a couple of things we look into if we look at D and the E together. And then we can see that the zinc oxide nanowire arrays, and so it has a higher potential, but also the decay time is the longest, right? So that gives more time for the charge carrier to recombine, right? While for the nanoforest, those two samples of the nanoforest, the decay time is actually shorter. So that's why also can help us to understand why the nanoforest samples have higher conversion efficiency. While here, if we pay closer attention, and then you will see that in terms of the decay time, the brush-like nanoforest actually has a shorter time and compared with the willow-like. So this is we believe that for the willow-like nanoforest, the branches are too small, so they could have higher defect density, and also because of those branches, are attached to each other, and that also gives provides the possibility for the charge carriers to combine in the willow-like nanoforest. So that's why there's a little bit difference here. So if we really want to put this into numbers, and then you will see the nanowire arrays, in terms of the photocurrent density. So then you will see that this willow-like nanoforest, the photocurrent density is almost 3 times of the nanowire arrays. So that means we can increase the photocurrent density by 3 times. And then if we compare with the literature data, and then we can see that even though our zinc oxide nanostructures are not doped, just pure zinc oxide, and then you can see that the PCE is almost the same as the nitrogen doped branch, the zinc oxide, which is this type of samples. So that really so give us confidence about this type of nanoforest. It really can improve the PEC performance. So that's one aspect. If I want to summarize it, there are several advantages of this type of 3-dimensional structures, right? So the electron diffusivity, several orders of magnitude larger than nanoparticles, right? And then the enhanced interfacial surface area because of these branches. Because of those secondary branches, and then in the connected conduction pathways, right? Because in these 3-dimensional nanostructures, right, the charge carriers can move smoothly, right? It's just like our freeway instead of our local streets, right? So freeway, there's no signal light, right? So we can go much faster. And though then there is a higher efficiency because of the occupancy of the large void spaces, right, by the branches. So that gives us the, those the advantages. So that's good, right? So that's not the end of the story. And as I tried to mention to you a little bit earlier, right, when we apply the nanoparticle, zinc oxide nanoparticle seeds, it is the second time especially, right? Depends on how we do the coding, right? If the concentration of the zinc oxide seeds is too high, right, then we will end with a lot of zinc oxide nanoparticles at the bottom of this nanowire arrays, right, which is not good, right? And so we've been thinking about how to overcome this issue, right? Because the images I showed you, right, most of them they are top views, right? So so we've been thinking about this, and also these nanostructures are the growing upward, right? So we've been thinking about maybe there is a better way to do that, right? For example, if I can make some zinc oxide nano fibers and then convert them to zinc oxide nanoparticles, and then we can use those zinc oxide nanoparticles as a seeds, right? And then we can grow branches on these zinc oxide nanofibers, right? And based on the parameters which we tuned in terms of the PEI concentration, in terms of ammonia concentration, right? So we can adjust the diameter and the length of those zinc oxide branches. So yeah, it looks interesting, right? So how do we get this zinc oxide fibers, right? When I was in Texas, so one of my colleagues, she has this type of forcing equipment, okay, and so so we can spin this by the centrifuge force, and then we get the fibers, right? So if you to help you to understand this, maybe you like these cotton candies, right? Some places they are still available, right? So sweet and it's nice, right? This is how actually exactly the same process for us to make this type of fibers. The only thing is for the cotton candies, we just try to use one connector, right? So we get this shape. Okay. For this processes here, we have those connectors surround this spinner. Okay. So we can connect them actually in this type of form. It's like the mats. And then, in those mats, if we use the electron microscope, then we'll see those fibers like he's showing here. Okay, of course, these are to get these fibers, right? We cannot spin zinc nitrate aqueous solution directly, so we need to add a polymer into it. So here we use the PVP as the binder. So we get these fibers, and then the next step is okay. Right, normally, we know this process, right? If we want to remove the polymer, we burn it, and that's what we did. And also at the same time, we are able to keep the nanofiber shape while we convert the zinc nitrate into the nanoparticles. And then the next step is the same as I just showed you earlier, right? Use the hydrothermal synthesis to grow the branches. And that's what we did. And these are the, the images, and we can see that, especially when the resolution is high, we can see this actually, these nanofibers are actually composed of nanoparticles, and then we can grow the branches. So I hope I'm okay, I'm not too slow here. Okay, anyway, so then we can confirm that, in terms of the crystal structure as well, and this is what we did, and then we did more characterizations, and then you will see this. We call, my students actually coined this name. They call it the caterpillar like branch zinc oxide nanostructures, right? So how do how did he started with this? If we look at the if we really look at the end of this, it's really like a caterpillar. Okay, so that's what we learned this, and also we did high resolution, and we made sure that which growth direction is things like that. Yeah, again, this slide shows that we can tune the branches, the diameter and the length of those branches. And also you can see that they are pretty dense on the surface of the substrate. So yeah, that's just the other way. So okay, so and then we did the same thing in terms of the photoelectric chemical performance. Since I already talked about similar things before, so I will not go to the details. But the samples we looked into this is, so the ANC means the optimized zinc oxide caterpillars. Okay, this is a zinc oxide nanofibers, and then this is the not optimized zinc oxide caterpillars. So you can see that for the optimized zinc oxide caterpillars, their performance in terms of the photocurrent density is much higher than the other ones. And then we also look at the conversion efficiency again. The optimized zinc oxide caterpillars show is the highest performance, and this number is not as high as the one we showed before, but it's high enough. And then we also did something similar in terms of the open circuit voltage decay. So this zinc oxide caterpillars shows the best performance. So to summarize this, and then we put everything together, and also we as I just showed you before, and then this is how the charge carrier moved to the substrate, right, into this type of connected nanostructures. And one important thing, as I showed you before here, is the conversion efficiency, and clearly we can see the difference between these different type of samples, right? And also at the same time is along the way, and there are other type of three-dimensional nanostructures used for the electrochemical conversion. The two examples I just showed you, these are from the examples I just showed you. This is from the literature as I compared, they doped zinc oxide with nitrogen. But at the same time, there are some other systems, for example, like titanium dioxide, people also made the branch and the nanostructures for that as well. But zinc oxide has its own advantage, many advantages. The synthesis is much easier. So that's what we aimed to conclude. So I mainly focused on two types of three-dimensional zinc oxide nanostructures, and so one is this nanoforest, and then the other one is this type of we call it the caterpillar-like zinc oxide nanostructures. So we proved that this type of nanostructure, three-dimensional nanostructure, gives the better electron diffusivity and enhanced the interfacial surface area because of they are interconnected. So the conduction pathway actually exists, and then it gives higher efficiency both in terms of the physical occupancy and also the internal light scattering. So that gives the better performance. So of course, with all this, if I need to appreciate all my students and visiting scholars, postdoc fellows, and in the past years, I'm always enthusiastic to work not just graduate students, postdocs or visiting scholars. I've been working with a lot of bright undergraduate students, and even a lot of high school students. And this summer, actually, I'm going to take 5 high school students, and that will be a lot of work. But I think that will be exciting as well. And of course, without collaborators and without the funding, and then none of this can be done. And with that, and if there are any questions and comments, please. I know there are some comments already. Yeah.
So, Professor Mao, great lecture. And but now there will be 5 minutes question answer session. I asked Professor Tokeer to ask someone from your side to handle the question answer sessions. Okay. Questions, I think, are in the chat box.
Thank you, sir. Dr. Ufana Riaz, please ask the questions on behalf of the participants.
Thank you, Professor Tokeer. I would like to thank Professor Mao for this wonderful, informative lecture. The first question that we have from the participants is, are there any TiO2 nanoforests?
There was some report. There was some reports, but the synthesis is much more challenging. As I showed here, I don't remember exactly the synthesis process, but there was reports.
The next question is that on using ammonia to control morphology of metal oxide nanostructures, the solution is escaped from the and it is difficult to control the solution, ammonia solution. So can we concentrate ammonia to control the morphology?
The ammonia concentration, you know, for zinc oxide is not to be too high. As I mentioned before, if it's too high, it's actually we will etch the zinc oxide. So it's just, you know, the pH cannot be too high.
Okay. And which deposition technique can be used for growing nanowires? And can we have any alternative to zinc oxide for growing nanowires?
Oh, okay. So let me get back to this slide. So I was trying to show that you mean to grow the zinc oxide nanowires, right?
Yeah.
So zinc oxide, you know, if we just want to grow nanowires, is we can grow hydrothermally. Is quite a common process. And here, of course, I'm showing to grow the zinc oxide nanowire arrays on the substrate. So that's why we start with zinc oxide seeds on the substrate. If we just want to grow zinc oxide nanowires in solution, we can just directly use hydrothermal synthesis. I hope that answers the question. I know you were asking other methods, but
yeah. I was about to say that. I hope that satisfies the participants' query, I think.
Okay. My point is the hydrothermal process, you know, as I show, I'm showing here, the conditions are pretty mild. So yeah. For me, I think it's more desirable to use this method. Yeah. Okay. Definitely, there are other methods. For example, the chemical vapor deposition techniques. You know, people reported that as well. Yeah, there are more physical deposition techniques as well.
Okay.
Yeah, maybe because I'm a chemist.
There's another question based on the deposition. It's which substrate are best to employ the deposition of metal oxides initially?
Let me see. ITO.
And the second part is that how can we prevent further deposition on substrate like your paper on manganese oxide and carbon?
Can you repeat that question again?
The first part was which were the best substrates to employ deposition of metal oxide. The second is that how can we prevent further deposition on substrate like your paper, which you have published based on manganese oxide and carbon.
Okay, so yeah, so here the substrate we use it is IDO, right? Because if we not for the supercapacitor, but for the electrochemical process, right? You know, it's better to use a transparent substrate. So I hope so. Then for the deposition of manganese oxide on the substrate, I believe they are deposition as well.
Okay.
So here, yeah, schematically we need to show that, but I don't think we consider that aspect. So I hope that answered your question. But
Yeah.
what I want to say is definitely I believe there is a manganese oxide deposit on the substrate as well.
Okay. And then there is a question on morphology. Which type of morphology is good for getting high surface area along with high current density?
So as I showed you earlier, you know, both of these zinc oxide nanoforest and those caterpillar structures both are very good. They have their, you know, have their pros and cons, right? So the caterpillar synthesis, you know, is much easier to scale up, while in terms of the PEC performance, so far it looks like it's a little bit lower than the nanoforest samples. Yeah.
There's another question based on photocurrent efficiency. That is, which is the best way to have high photocurrent efficiency?
Based on the samples we prepared here, if we really look at the data, which I want to show you here, so you see this one, the willow-like zinc oxide nanoforest, you know, in terms of the PEC is almost 0.3 at this current, at this potential. And then for the caterpillar samples let me see, I think I better stay here, So at a similar potential, and the conversion efficiency is only about 0.2. So in that way, I would say that the nanoforests have better performance.
Dr. Ufana, there are a lot of questions in the chat box. Actually,
yes, I would like to wind up.
And Professor Mao will be with us for next 7 days. So the participants may ask the questions later on. So I think we should move to Professor Ganguli because actually
Yes,
Professor Chattopadhyay has come and is waiting.
Yes, I'd like to invite Professor.
Right. So thank you, Professor Mao, for answering all the questions. And we're extremely happy for your lecture. So we all once again thank you for the fine lecture that you gave. And anyway, you will be continuing with this program next few days also, right? So thank you again on behalf of the organizers. Thank you, Professor Mao.
You're welcome. Thanks for the opportunity.
Thank you. So yeah. So now, Professor Tokeer, you want to start the next lecture?
Yes, sir. The next lecture is by Professor Arun Chattopadhyay, sir. Sir, and sir, I request you to please introduce Professor Chattopadhyay to the participants, sir. Please welcome to Arun, sir.
Yeah. So, welcome,
keep it short.
Professor Chattopadhyay. I will keep it short. Professor Chattopadhyay is currently at IIT Guwahati, and he was the chair of chemistry and is also started the nanotechnology group at IIT Guwahati. He studied at Presidency College, then IIT Kanpur, then did his PhD from Columbia University, and then postdoc at SPARC. He's a fellow of Indian Academy and Indian Science. Also got the and a good human being, good friend of mine. It's always nice to be conferences. Very honest and very good. I wish that he becomes director of IIT Guwahati. So welcome, Professor. And for your
thank you, Ashok. Can I start?
Sure.
So first of all, there may be some disruptions because there is no power. Somehow the rain has caused some problem here, but I will try to best. If there is a disruption, please be patient. Okay, next, let me start. First of all, I thank Ashok Ganguli for introducing me. And most importantly, I thank Tokeer Ahmad for inviting me, for organizing the conference. I have been following most of the lectures since yesterday. They're going well, and I'm happy that a lot of students, faculty members, and scientists are benefiting from this project and the seminar series. I hope the up and coming seminars in next few days will be also very beneficial. Next, I would like to thank Ministry of Electronics and Information Technology, Department of Science and Technology for funds. First one being major, second one is a fellowship. And Department of Biotechnology also has sometimes supported our work. So I will start as a teacher. So far you have heard from distinguished scientists, extraordinary lectures. Now it is your time to learn, to study with an ordinary teacher. I will speak like a teacher. So where do I start? I start with your questions. As suppose I am in high school, suppose I am in undergraduate student, suppose I am a master's degree student or first year PhD. I ask the question, what is the research? Where do I start? How do I start? What is the aim? The simple answer is, whatever you do in science is research. And you in the world only know what you can do, what you want to do, and what you will be able to do. No one else in the world actually can help you much. They can help you circumstantially, they can help you with materials and sometimes ideas, but you have to come up with ideas, you have to implement the ideas, and then you have to pursue them till it is complete. Now, all of us as students, as teachers, as scientists want to solve problems. What are the problems? The problem that afflicts us. Currently, everybody wants to solve COVID-19 problems. Before that, cancers, infectious diseases, and others. Even simple understanding of diseases people want to solve. So how do we approach? I will give you step by step, very basic of that. In the current case, this picture you see is how do you implement a nanomaterial which has nanoscale dimensions, but it can function using magnetic field, electrical stimulations, chemical, biological, and that is called multifunctional nanomaterials. That we had worked on sometimes back, but I will not focus on it today. So what is the idea for one of the dreams of every scientist who wants to pursue in this kind of field? Tokeer defines as material science, others also define that way, and engineering, is that I will develop one nanoscale material which will go through human body, especially blood circulation system, and cure all the diseases and inform me what is happening inside. As of now, that is left to be discovered, invented, and to be developed. So those young scientists there is a lot of things that can be done in future. So one of them is microscopic robots. They need not conventional principles, new principles to be developed, new working principles also. That is, first is basic science, working principle, how they will be guided, and all of these they are yet to be discovered. So we are still far away from completion of the dream that there will be a robot that will go through my body and cure me all my problems. I can get to live for 150 years. Now, why do we need that? If we are born 100 years ago, by age 18, most of the people will have 2 kids and they will be adult. Now, society thinks that 18-year-olds are young. 100 years from now, that will be even younger. Why? 100 years ago, people usually died around the age of 50 or so to 60. Now people are living till 80, 90, 100 plus. 100 years from now, people will be living for 150 plus. For that, we need to develop science. We need to develop healthcare systems. Whatever we do today, small things also may be having important contribution to those futures. Now let me begin. This is the introduction that as many scientists as possible can contribute, no matter how small a scientist is. Any small idea can be useful as at least a reference for others to learn.
I'm sorry, there is some problem with the system of Professor Arun Chattopadhyay. Please wait. He will be back.
He told me that he has issues in connection.
Yeah,
Connectivity.
yeah, connectivity. He is trying to reconnect. There is low bandwidth. That's the problem. Maybe he will join soon. Yeah, I think he is coming. Sir, your mic, you have muted your mic. Yes, sir, okay. No problem, sir, no problem.
Oh, is it muted?
Yeah,
Okay.
you are muted.
Can you see my screen or no?
We are actually seeing you, sir, not your screen.
No, no,
You are
you can't
visible
see
to us.
Okay, one more time, one more time.
No, no, now it
Yeah,
is
yes.
sharing, it is sharing. Just wait.
I am not able to see. Yes, now it is all is well.
No, it is coming. Yeah, now we can see that.
Right. Thank you. I am sorry. Okay, all is well now.
All is well.
Somebody had reset the UPS button. That is why it got disconnected. All right. So, as I was discussing about, you have gold bulk, you have silver bulk, you have copper bulk. The properties of each of them is different from others. And these properties are decided by nature. We have absolutely no control over their properties. So, but from the beginning, so atoms, we don't have control. Bulk matter, we don't have control. Everything is decided by nature. So what do we do? Just 1 second. I will just 1 second. I'll just turn on my. So what do we do? I will give you examples. Alchemists thought they could transmute any matter into gold. And Newton spent a lot of time in boiling mercury to convert into gold. That was not successful. Now we know why. You need to understand nuclear physics for that. Not enough energy. Chemically, it is easier. So how easy it is? I will give you the example. All of us drink a lot of water, H2O. All of us also need to drink a lot of water because most of our body is made up of water. The chemical formula is H2O. Now you add to that 1 carbon, 2 hydrogen. What is the chemical formula? CH3OH. What is the name? Methanol. If you drink that, you're not going to survive. First, somebody is going to get blind, then somebody is going to die. So chemistry experiment-wise, it's not a good experiment. Chemist said, okay, you made a mistake by adding 1 carbon, 2 hydrogen. You add now 1 more carbon, 2 more hydrogen. So what happens? It becomes C2H5OH. 100 years ago, that was used as medicine for Spanish flu. Now that is used for evening enjoyment. Right? Samwali dawai, different dawai. So that by changing adding 1 carbon, 2 hydrogen, you are changing properties of matter. That's why chemistry was so powerful and still very, very powerful. How? If you inhale benzene, chances are that you will get cancer after some time. But if you add 1 carbon, 2 hydrogen to it, it will become toluene. And toluene is safer to inhale than benzene. So chemists this way change many things for last 200 years, since 1827 or so. So that chemistry people understood that you can change the properties of matter by changing the chemical bond, number of atoms, and then orientation. Left hand is different from right hand. So these, in last 200 years, chemistry has mastered. But science belongs to all. So physicists want to contribute, engineers want to contribute, not only chemistry and biology people, but they also want to contribute. So what is it that will capture the imagination of everybody, and everybody in the world can make a contribution? It's a 4-letter word. That's a good word. Nano. What is that? I will explain to you. Nano, what it is, if you have matter in dimensionally very small, how small? you cut your hair into 1,000 pieces, 1,000 pieces. Now you will say it's very easy, go to a barber shop and cut it. Not that way. Perpendicular to that dimension. Not in that dimension, the way barber does. If you had a knife, very slim, cut your hair into 1,000 pieces, you will arrive at each piece with a diameter about 50 to 100 approximately nanometers, depending on your hair and quality. That's nano. Right. Now, what does it give? It gives you dimension dependent properties. What is that? You change the size, the properties changes, color changes. You look at the screen, there are nano rod, nanomaterial, size, shape. You change the shape, change the dimensions, everything changes. These new properties of matter that can be controlled by everybody. How? Chemists can contribute, bottom-up approach. Biologists can contribute, bottom-up approach. Physicists and engineers can contribute, top-down approach. Now, there is a field where everybody can participate, everybody can contribute, and everyone can fulfill his or her dream. That's the idea of nano. It's new, it's for everybody. I must emphasize here, when in the time of Newton, even in the time of Einstein, Marie Curie, science was very exclusive. Not everybody could do science in those days. Only very few people could pursue and publish science. But we are living in a very new time. Anyone born anywhere in the world can be a scientist, can make important contributions. Apparently, anybody can say scientists' contribution is not important, but I must emphasize that no matter how small it appears at the moment, the contribution, everybody's contribution is important. And so I urge all young students, faculty, start. Science is for enjoyment. Science is what you want to do, not what others want you to do. So let us start. In our laboratory, we work on many topics. What is the principle of the operation? Our principle of operations are that students are queens and kings. I am their servant. So they decide what they want to do. They decide how long they want to pursue on a work. I tell them possibilities. I tell them that first principle of the laboratory is that you must be honest, honest, honest. If that is there, everything else is easy. It is important. I tell them that it is important for students to be honest more than teachers, because science is carried out by students. And if students are honest, science will remain honest. So it is important for students. So I teach them first, you must be honest. I can solve problems if you are honest. So that is the first thing I teach all my students. Everything else, I suggest a problem and they solve. What is the other principle? Each one will work on probably a new problem, different kinds, so that in her or his life, she or he can go into new field, create new field. So we work on based on that, atomic clusters, nanoparticles, carbon dots, quantum dots, molecules, chemical reactions, all of these you will see. I will just quickly go through. Some of the slides will be faster, some of the slower. But I urge your patience and see how a laboratory and science can run guided exclusively by the students. One second principle I ask the student that you should charge at me, not I should charge at you. Only student must question all the time. I must answer, but at the same time you have to answer. If I answer all of your questions, I become smarter. That is not important. Students have to become smarter. So you have to answer your questions too. I am only there to help. So students have to challenge the teachers. That is very important. And as a teacher, I always like that. Next. So Science, before I go to science, because everybody wants applications, government wants applications. Tomorrow morning it should go to the market without knowing that it cannot go to the market. Market doesn't want it also. Nobody wants to understand that if you have a technology today, it may or may not go to the market. It's a different forces. Market is a different force. But still, some technology that is born out of science. I will give you examples. So some time back, I had an idea that you should be able to detect a disease by thumb imprint. Means you put your thumb, just like signature, many people do, who don't know, who are not literate. And that molecule transferred from your thumb should be able to tell what disease one has. So we demonstrated one. You know, when somebody has jaundice, hyperbilirubinemia, at that time, the bilirubin concentration on the skin also is very high. So we developed a method to detect the disease, hyperbilirubinemia. Excess of bilirubin, it's called, in popular terms, it is called jaundice. So what happens? Suppose I have on the left side a film made of polymer with material called gold nanoclusters. If you have a polymer embedded with gold nanoclusters, a solid, dry film like a paper, it will appear yellow, orange in presence of UV light. Then you put copper salt into it, the color will vanish. Copper ions are quench the fluorescence. Moment you put a thumb imprint of somebody who has jaundice, it will come back. So you have a simple way, at the bottom it is demonstrated, to detect hyperbilirubinemia by just thumb imprint. So you have, Tokeer, you keep yourself on, so at least I have one person to see. Or Ashok, one of you.
Okay, sir.
Okay, so I can talk to one person at least. So if you are tired, then you switch off. Otherwise, one of you, it will be easier for me to communicate. So, or you ask your student or somebody to be there, or any of them.
Sometimes actually, sir, speaker may become interrupted by looking the screen of others.
Okay. No, I am very happy. I am very happy to see somebody, not on the blank. I cannot teach on a blank screen. That's what I have been. Okay. Earlier for students, it was icons. Their faces were not there. In seminars, at least some faces can be there, like you have arranged very well. So copper ions changes the luminescence from orange to nothing. You put thumb imprint, it will come back under the UV light. How does it work? Copper ion quenches the fluorescence. Copper ion, if you put thumb imprint, if you have excess bilirubin, copper ion interacts with bilirubin to form a complex. So that copper is no more available for quenching. Your original luminescence comes back. So this coming back, this is a new way also of detecting. Normally luminescence quenching is the way, but this is reverse way. We have filed 4 patents: European patent, Chinese patent, US patent, and Indian. Indians will be most difficult, but Chinese is done, European is done. We are waiting for the US patent. This takes a long time. So these we are transferring to a company also, possibly. The company is a little slow. This is technology 1. Technology 2, this is the demonstration that hospital patients put their thumb imprint. We have taken the pictures that it works. How it works? If copper salt removes the fluorescence, luminescence, thumb imprint brings back. That's as simple as that. You can record that with the camera and analyze. Next is, I will talk about the student, is very smart chemistry student. Then I have, because we have a center, interdisciplinary center, we have the advantage of having PhD students from different fields.
Some connectivity issues. Yeah.
Is it okay now? Can you hear me?
Yeah. Yes, sir.
Okay. So Sunil Kumar Sailapu from Visakhapatnam, he worked on devices. He is an electronics engineer in collaboration with Dipanjali, who is a biotechnologist. I will describe to you. So what was the device? This device is for PCR and protein analysis. If you want gene and protein analysis, this device you can use. These devices use nanotechnology, means gold nanoclusters, and all these gives you beautiful, comparable to commercial devices, very cheap, and you can combine with your mobile phone, get all the results. Those are all done by primarily one student, the device, biology part in collaboration with another student, Dipanjali. That is device one. He also developed, Sunil also developed another device for biologists. What is that? That is for photodynamic therapy and colorimetric assay. You see what is being held? This is a real device for he is developed. This is typically 96 wells are there. It means one has to develop 96 UV visible spectrophotometer. So you have in that 96 UV visible spectrophotometer, light source, detector, all connected to devices and then to the computer and mobile phone. And they will, what will they give? That if some new materials you develop, is it good for photodynamic therapy using LEDs? Is it good for colorimetric assays? You can do all the colorimetric assays or not. So those analyses could be done using this machine. I think we have filed an Indian patent. Patents are too difficult. That is why publications is easier. We now are preferring publications, but this is the third device. What is the science behind some of these? He also developed a very interesting concept. I discussed in the beginning that how do you send a robot inside the body and functions. What Sunil developed, this is a Faraday coil, copper coil. If you have nano robot, means this is micron scale, but it has nanoparticle in it. And if you have a liquid medium where it is reactive, means chemical reaction happens. Chemical reactions lets it move autonomous, called autonomous motion. Moment it goes through this Faraday coil, it will produce electricity because it has magnet. So you have a chemical reaction driving the motion of a microbot containing nanoscale particles and magnet inside. And then as it goes through, you can see electrical signal as it goes through the coil, and it can light LEDs. So you can generate in situ electricity required for motion of a microbot inside the body, and then it will move, produce electricity, and it will give you light. One of the ways we have demonstrated light. You can make other functions too. What is the idea? It is not that tomorrow we will develop the robot and all. It will work. It is the idea that as scientists, we must contribute new and original ideas. What is there? That you can run a microbot with nanoparticle using chemical reactions as a fuel and generate electricity. So in future, you develop microbot. Here is a way to generate electricity to run the microbot. This is the science part of it. Okay, now let me go to pure science now. I have told you about technology. So, Tokeer, when should I stop? Tell me. I'll plan accordingly.
12 o'clock. 12 o'clock.
I should stop at 12 or discussion should stop at 12?
Actually, we need 5 minutes time at least for the question answer session.
Next is 12:15. Next is 12:15. You tell me,
Yeah,
you decide, I'll follow.
Sir, yeah, 12:15. 12:10 you can continue. 12 o'clock.
Okay, for the moment, I am planning to stop at 12 for the moment. Let us move forward that way. Okay. Okay. So science. This is at the heart of our work, our life, and lives of so many students. What is it? As I told you before, just like atoms form molecules, can you have an assembly of nano to another nanoparticle, and new ideas should come out. New functions should come out. I'll demonstrate some of those. So where did we start? Long time ago, more than 10 years ago, I had a student, Raihana. It was very difficult to, so I told her that you study chemical reactions involving nanoparticles, especially quantum dot. Means, if you change the oxidation state of a quantum dot or constituent particle, ion, it should behave differently and it should bring new properties. It took me 2.5 years to convince her that it is an idea, and only when one paper in Nature came, she thought that it is worthy. So she started 2.5 years after joining PhD. What did she develop? If you take a particle, quantum dot, say, that is made of cations and anions, zinc sulfide, zinc oxide, you have heard yesterday, or any other semiconducting material or doped semiconductor. If you put just simple ion removal, ion exchange resins in the medium, it will remove the ions, cations, and it changes the properties of the quantum dot. The first experiment she did showed that you can change the properties of quantum dot by changing by removing the ion from the surface of the quantum dot. And that was later used by another student who is now a faculty at IIT Mandi, Amit Jaswal, to detect, to sense mercury and other ions comparatively. She also later on worked on oxidation and reduction. If you oxidize one ion inside a quantum dot, does it property change? Well, it does. We found out the emission characteristics of the quantum dot can be changed back and forth by reduction and oxidation. That's what her contribution. That's how we started. Then came 3S. So I told them, you have to go a little further. What did they work on? They work on here. So Rahana was here, oxidation reduction, ion exchange. 3S work on complexity. So if you have a quantum dot made of, say, zinc sulfide, zinc oxide, or any other similar material, if you have zinc ion on the top and put an organic ligand suitably, in this case 8-hydroxyquinoline to start with, you can have a complex on the surface, and you can have at least two properties on the same quantum dot. We defined this quantum dot complex. It's a composite material made of that. From there, we have shown that you can have material that is heat resistant, means if you increase the temperature, it is still stable, thermally stable. You can have solubility issues resolved, means water soluble, water insoluble, whatever you want, you can do. You can transfer from one medium to another, and you can study chemical reactions between two nanoparticles. Fundamental science you can do. So these took some 10 years or so. Now we are finishing those chapters. One final student, Mihin Manna, he is completing those. We have shown a very nice targeted bioimaging. What is that? If you have a quantum dot and then complex inside which a magnet is there, you can actually have a new composite quantum dot complex and use a magnet to move, and then let them react and give you new ideas, new signals. We could detect cells, components of cells, molecules using this. In addition, we could generate white light emitting quantum dots. That's a new idea we have proposed. So that is part of quantum dot complex. A new electronics student, Kosturi Gogui, she is working on electronics applications. What is the electronic application? Can you detect two wavelengths of light, one with the quantum dot, another with the quantum dot complex? She just recently completed the work. You can actually detect two different wavelengths of light by using quantum dot complex and quantum dot electronically. Photoelectronically, you need light, interaction with the light also. Okay, that is chapter, that is one chapter. Next is, I have told students that can you pursue reactions in between nanoparticles. If you take a gold nanoparticle, it is plasmon active. Now, it will only give the plasmon, that means electron oscillating electrons. And if you have a molecule on it, there is something called surface enhanced Raman scattering. You will get, here you see one without molecule, the molecular signature in Raman, put on the surface of a single nanoparticle, you will get improved significantly. But if the molecule is in between two nanoparticles, the signal that is called hotspot means the electric field due to both the nanoparticles in between is enormous and improves the quality of signal. So you see green, that is in between two. So I told the student, can you pursue Raman spectroscopy of one molecule put in between two gold nanoparticles? So her name, she started, Anushree Datta. She was very reluctant because most of the students, you know, who joined me, they want to do biology, especially in chemistry. From chemistry background, whoever joins, they want to do biology. They think biology is very alluring, attractive. I should do biology project, disease detection, disease cure, this, that. And biology students want to do chemistry. So I use both of them and tell them, okay, you try. So chemistry student, I send them to biology lab and ask them to do biology. After some time, they realize biology actually is very hard because you need to wait for 18 years to become 18 years old. You cannot become 18 years old by any other means. You need to wait for 18 years. So biology is not so simple, so they come back to chemistry. But biology people are smart. They think that chemistry means A plus B plus C you mix, you will get something new and you can have nano and then you can publish a paper and apply into biology. So they also try that. These two combinations we try. So she was interested in biology. So it took me 5 years to convince her that she can try. So we reached a midpoint. She will do biology and chemistry both, physical chemistry, and she will parallelly pursue both the projects. One in biology, one in physical chemistry. Biology she did, that was published in ChemCom. Physical chemistry part I will describe because I like it more. What is the idea? Is that, is it moving? Yes. So for that, you need to be a synthetic chemist. What is the idea? You need to put one gold nanoparticle here. You need to put another nanoparticle here, a molecule in between. Just one molecule if possible. So synthesize a molecule, European complex, such that europium will be binding to oxygen of the ligand molecule because europium is oxophilic, and thiol group will be here and here. And gold nanoparticles love thiol group. So that we reached, I don't know, I think we have dimer, many population. We found out that we are reaching close to theoretical limit. These dimer separated by the distance of a single molecule. Large number of populations we have. I am putting it as small signal, a small number, but we had done many TM. So what if you see, this is the chemistry idea. One nanoparticle of gold in between a molecule. Now, if you put a laser from the top and the molecule, single molecule here, you cannot detect so easily, many of them. So we put STM TARS, deep enhanced Raman spectroscopy. What it means? This is a gold tip, this is laser, two atoms, two nanoparticles in between one molecule. So all of this will contribute to give you a signal. So scanning, tunneling microscopy tears, SFM, Scanning force microscopy she also did, TERS, both of the two different principles of operations. And she got beautiful signals after 5 years. So if you see, if you bring the tip below, signal goes up. If you bring the tip above, move up, signal goes down. So this is tip enhanced Raman spectroscopy of one molecule. Most likely she is the first one in India to have done that. I have not come across any other publication. Raman spectroscopy possibly of single molecule. It took a lot of convincing her, but she learned almost everything. I'll tell you how this works. Because it is single molecule, STM and others, she had to work 7 days a week, night time only, when there will be no noise, no motorbikes, no movement in a lab, no one else should be there, almost dark, and work for 7 nights continuously to get a good signal. And if you make one mistake, you lose 20,000 rupees because tip will cost you that much. So that's, she finished and these work. Then what we did, we again pursued now because next students found that it is too hard. Srimanta, his name, is too hard to do, and so they want different chemistry. So now we are pursuing reaction in between nanoparticles called plasmonic hotspot. What is that? You take a molecule, put it in between there, and make them react in presence of light and plasmonic field, and you produce the product. So you pursue this. You first see you have linearly arranged the rod under TM using the molecule. Then you probe the products, rate constant you then measure. You found out that when you have dimer or higher, the rate constant is higher compared to in, that means hotspot generate faster chemical reaction. And you can have dimer. We are pursuing interesting chemistry there. That will take 1 year. It takes long. Each of these work takes a long time. You can see this is how we pursued each reaction and how Raman it goes up and down. So that part is Raman. Molecules in between two gold nanoparticles, typically on nanorod. Next come a very different idea. She is the one, Shrestha, she did first thumb imprint. Then I told her you pursue science. So nanoparticles, two nanoparticles may not be exactly identical. Two molecules are identical, two atoms are identical, but two nanoparticles may not be identical. But two clusters can be. Means atomic cluster. If you take 10 atom cluster, 20 atom cluster, 15 atom cluster, they can be identical. They have to be stabilized by an organic molecule typically called ligand. So this is where she started. What was the question? If I take, this already was known, that you can have atomic clusters in liquid medium. We have done also on different contexts, in different contexts, and then put ligand, then have some group on the ligand side that it can form complex with zinc ions. Can you make organization of clusters through complexation reaction? That was the idea she pursued. So she showed that you can actually take AU14. We have found out structure and all that will take long time to describe. With ligand, then you organize in 3 dimensions using zinc. If you pass hydrogen, this is colored in presence of UV light, fluorescence. In presence of hydrogen, color vanishes. You remove the hydrogen and it goes. So what happens? Theoretically, it was possible that gold atoms in gold clusters can split hydrogen molecule into hydrogen atom, form hydride, and thus the color goes. Moment you reduce the pressure, then hydrogen again come back. So you have storage, sensing, and recovery demonstrated. So we had, I will go quickly, we had single crystalline materials. Through TM, we could find out most of the parameters. Sometimes also we got XRD, but very rarely. We had to, this took a long time to establish the structure. 3 months for one structure it took. But this was the idea that you can store and recover hydrogen. That is the idea one. That cannot be done using clusters. That can be done using assembly of clusters. All right. Next is, you see, nature has gifted us asymmetry. How? You can only shake a right hand with the right hand, left hand with the left hand. You cannot shake your hand with yourself. So you have to always shake a hand with somebody else. That is asymmetry to me. But Indians discovered that, or invented, you can put two palms together and call namaste. So that is also possible, right? That is, there are a concept called 2-point interaction, 3-point interaction, multiple interactions are there. In inorganic chemistry, it is there. So here, she put ligand. Now we have to do ligand chemistry. Change the ligand, asymmetric. I just quickly rush through this. We have done all analysis to establish the structure. Trust me, without that, it will not go through the journals. We found what, depending on the ligand, these same AU14 will have a different structures energetically. These will reorganize in 3 dimensions, a beautiful crystalline material. If you start with left-handed organic molecule as the ligand, it will form one type. If you start with right-handed organic molecule as the ligand, stabilizing the cluster, it will form another. And you can use this for 3-point interaction and not only sense enantiomers, but you can isolate them one from the other. We have shown optically many ways that I will just rush through. So this is application 2. Third is, one of the problems, there are many problems, toxicity issues. Nanomaterials is still not applied to human body, is that nanoparticles are so large compared to molecules, it cannot come out of the body. Suppose I use smaller nanoparticles like clusters, which are 1 nanometer, similar to molecular dimensions. Assemble them, it will go to the cell, disintegrate, does its job, and then comes out of the body. This idea we demonstrated using assembly of gold clusters in several papers, that you can have assembly of gold clusters with a ligand that is a biomolecule and medicine. It can be. And then this is the beautiful materials we have developed, structure, and then electron diffraction. All of these we analyze and we propose 3-dimensional structures. We put inside the cell. We have shown it disintegrates. And with time, that we have also shown, because of generation of reactive oxygen species, it does its job. That is called mitochondria targeted therapy, and then comes out. That is biology application of science. So science is the primary, application is essential and reality and fulfillment of an ambition. Next is that, can I have carbon dots? Carbon dots, you have graphene, you have fluorine, you have carbon nanotubes. Carbon dot is poor people's carbon nanotube or anything you can generate. One biology student in our laboratory first developed that you can use a simple microwave to generate carbon dots. And we then showed that when you take bakeries like bread, bun, chocolates, gur, biscuits, cornflakes, you are eating every day nanoparticle, that is carbon dots. So that is happening for the last 5,000 years. We showed that. And that is why these carbon dots can be used for health purposes also. But that is not the aim here. If you take, first make it crystalline, because we need exact structure. So if you put phosphate group in it, it becomes crystalline and you can have heat energy storage application. I am not giving the earlier work. We have done heating of water also, that's separate. But you can organize, you can have a crystalline carbon dot. Then you can have zinc and organize, and that will give you very nice supercapacitor applications. We have done the structure, we have done the analysis as supercapacitor, and here is the table. You can see when you have 3-dimensional structure, its performance is quite good. Not the best in the world, but the idea works. If you take without assembly, it is less. And then this is activated carbon dot. This is without assembly. This is with assembly. This is number one. Number two, just we have found that you can also have as carbon dioxide sensing. Maybe in future we'll do reaction. For the moment, electrically now you can sense carbon dioxide using assembly. This is just accepted, and for the 65th birthday anniversary of D.D. Sharma, it is accepted in JPCC. The last week, yesterday I only uploaded the Ganguli proof. So you can make super crystalline, means you have carbon dot crystalline, arrange into another higher order crystals, super crystalline arrangement, and you can have beautiful carbon dioxide sensing specifically carbon dioxide based on that. Now I'm coming to close, so within 5 minutes I'll finish. Molecule-based nanotechnology. Last I will talk about that. Other we'll discuss sometime in future. Now the idea we are pursuing now, can we use molecule to build nano? So here again, Shrestha, the extraordinary students, he started, and other students are starting, or Chismita is another one. What is the idea? You take molecules in a liquid medium. You decide which molecule to take, allow them to crystallize or grow into nano phase. As it is, you will see new properties arising. So bulk material is weakly luminescent, but nanoscale strongly luminescent material. You can have UV visible with time. You can have luminescent material, and you see beautiful crystalline materials with time. It grows polycrystalline mostly, but based on molecule, you can build nano, and they give you new optical properties. In this case, we are developing other physical properties also. These are time evolution of crystallization. In high school, we studied how a molecule becomes crystallized. We want to show those band evolution of the band as a function of size. So we have shown to some extent, and structure we have to develop. We have developed what is the unit structure of the molecule. This is zinc acetate with ascorbic acid. It forms a beautiful crystalline material that gives fluorescence, and others we are working on. So this requires, so in future we have we are working on many of these fundamental ideas. First is science, then will come technology. So I will stop here, but I'll tell you other students are working on that I did not describe. She is working on, Devasri is working on bacterial bots. You will have bacteria carrying nano, going from place 1 to place B. At place B, it will deliver drug to cells, to organs. Initial success he has got. Then all of them are working on either quantum dots, assembly of nanoparticles, new properties, assembly of molecules in between nano, or assembly of nanoparticles. So there are other students, these are biology students. She is working on application of nano to biology. I have talked about her. She is working on and whether you can have new molecules which will be replacing antibiotics. That Konika is working on now. I thank Siddhartha and Anumita for collaborations. I thank again all of you for kind attentions. I think it is exactly 12, and I am happy to be with you. And I am really grateful for Tokeer's invitations, and I can have some discussions with you if time permits. I'll be happy with that.
Okay, I now hand over to Tokeer. I have a meeting now. So thank you, Arun. All the best. All the best. Give now. Okay. All the best.
Right.
All the best. Bye.
Thank you so
Thank
much.
you,
Sir.
Ashok.
Thank you so much, sir.
Yeah. You can carry on today.
Yeah. Okay, sir. Bye-bye, sir. Dr. Ufana Riaz, now you can take the questions from the participants, and sir will give the satisfactory response. Please.
What did you say? Oh, I hope the lecture was useful.
So very useful. Actually, the time actually we are filling the time is short. I should extend your lecture for 2 hours. Sir.
And now in future we'll have.
Yes, definitely, sir.
Maximum I have given for 4 hours, but students' patience also is required. Online 4 hours is difficult to keep patience.
Very difficult. Dr. Ufana.
So now, sir, we are coming to the question and answer session. So the first question is that can we use silver nanoparticles instead of gold as surface plasmonic resonance also shown by silver?
Yes, very much. Silver nanoparticle, lot of people have used already before gold because it gives better signal than gold. But only problem is theoretical understanding whether silver or now it is now understood that silver oxide might be formed on the surface of silver nanoparticles. That silver oxide might play a role, so you don't understand as much as if you take gold. Gold doesn't normally get oxidized. So theoretical understanding is that silver nanoparticle, you may say, on the surface silver oxide form in ambient conditions may play a role or during synthesis. So silver nanoparticle, yes, some people already have done.
The second question, sir, is that does nanoparticle reaction need us to work and think on subatomic particles to understand their mechanistics?
Simple answer is no. Of course, role of electron, chemistry teachers ask from high school, the role of electron is important. Oxidation state important. So if you have that argument, the number of electrons, oxidation state, they are important in that aspect, yes. But generally, simple answer is no.
The other question is that, sir, if we perform any organic transformation reaction by considering the plasmonic hotspot, a catalyst surface, will it work efficiently to optimize transformation reaction?
Ideally, theoretically, yes. There is no reason in theory it will not be better than conventional. But what happens? Somebody has to spend 10, 20 years to develop the entire field, bring it to the reality. That is still not effective because you need to know organic chemistry, you need to know nano, you need to know physics, you need to have machines. So those in principle and in practice, yes, you need to work on it.
The other question is that, sir, by which technique can we analyze the catalytic site if we use plasmonic hotspot?
First is that reaction we follow by Raman spectroscopy. That is the easiest now. Live you can, because everything in the world now they use the word live. You can monitor a reaction live using Raman. You can also have electronic spectroscopy, photoelectronic spectroscopy. Those will be also useful to study at the level of single molecules. IR spectroscopy also you can use, UV visual also you can use. Continue, next question.
So these were the questions that were given by the participants. I think we
There
have only these questions.
There were 2 more questions in the chat box.
Subatomic particles one, sir, has answered.
She is very smart. She remembers everything.
Yeah, move on, Dr. Fan.
So, sir, we would like to thank you for such an informative lecture, and it was very interesting to see the graphical part especially and relate it with the applicational part.
Thank you for your enjoyment of the lecture and of your full support. And I really enjoyed being with you.
And very informative.
Yes, you continue.
It was interesting and informative as well because of the interdisciplinary part on which you have focused the entire lecture.
Now let me conclude by saying 1 or 2 sentences.
Yes, sir, sure.
So everybody wants, see, this is all students want to jump to nano from undergraduate level. And why? Two questions will be answered. Why nano took so long to come up? Though Michael Faraday realized that in 1857, why it took so long? See, physics had to be developed, probe had to be developed, requirement had to be developed. So, quantum mechanics had to be developed, thermodynamics had to be developed, electricity magnetism had to be developed, chemistry method had to be developed. Finally, now we have reached a level we can synthesize top down or bottom up. Either way, we can reach nano. So we had to wait so long. But fortunate part of it, we are born in a time where nano has been developed or is developing. And it is our good fortune that we will be able to participate. More importantly, that all students must first pursue basics. You have to know physics, you have to know mathematics, you have to know chemistry, you have to know biology, you have to know engineering. Then you can reach nano understanding. It takes typically 10 years, but you are very smart, you can be shorter. Now you can ask. So good luck for your future. If you do well, all of us will do well. Meaning, future generation must do better than our generation. That's the hope, that's the aim. Thank you. Thank you.
Thank you so much, sir. Thanks for coming and thanks for accepting our invitation. And our participants are very much happy. We are giving you the compliments. And sir, in the next time, you will have your more time, sir. Thank you so much, sir.
Okay. Thank you. Bye-bye.
Bye-bye, sir. Dear participants, the next keynote lecture will be delivered by Professor A.K. Tyagi, BARC Mumbai. And we have 5-6 minutes more. So probably in a couple of minutes, Professor Tyagi will join. So please have some patience for 4 to 5 minutes, and then we will start our last keynote lecture before this. Thank you.